ketones or aldehydes can condense with secondary amines to yield enamines. An enamine is a functional group with an amine bonded to an alkene carbon. Much like hydrate, acetal, and imine formation, this reaction relies upon nucleophilic addition across the carbonyl pi bond. The reaction requires gentle acid catalysis and is freely reversible. Therefore, the position of equilibrium is often controlled by driving off water to push the reaction toward the enamine. Alternatively, an enamine can be hydrolyzed using excess water. The first phase of this reaction is hemiaminal formation, and it is indistinguishable from the first phase of imine formation. The carbonyl oxygen is first protonated, and this enhances the electrophilicity of the carbonyl carbon. That in turn invites the attack of the amine on that electrophilic carbonyl carbon, and the carbonyl pi electrons are displaced onto oxygen. The ammonium ion thus formed sheds a proton to the medium to provide the hemiaminal intermediate. The hemiaminal, though, reacts further to give an aminium ion. This occurs when the hydroxyl group is protonated and water, as a good leaving group, dissociates from the molecule. An aminium ion is thus formed, and its two resonance structures are shown here. It is only in the very last step of the mechanism that this reaction differs from imine formation. Since the nitrogen has no proton to lose, a proton must be instead lost from the alpha carbon. And as that happens, electrons are pushed onto nitrogen to neutralize its charge, thereby forming the enamine. Enamines, much like acetals and imines, are susceptible to hydrolysis in aqueous acid. The hydrolysis mechanism is the exact reverse of the mechanism for enamine formation, and it begins with the formation of the hemiaminal. That occurs through initial protonation of the enamine. The enamine is protonated so as to make the more stable resonance delocalized cation. Water then nucleophilically attacks this cation, pushing electrons onto nitrogen. The oxonium ion that results then loses a proton to provide the critical hemiaminal intermediate. The hemiaminal is still reactive under these conditions and degrades to the original carbonyl-containing substrate. This happens when the amino group is protonated. A good leaving group, namely an amine, dissociates then from the substrate. The cation that is formed is resonance stabilized, and loss of a proton from the more stable resonance structure results in the reformation of the original carbonyl-containing substrate, which in this case was a ketone. Now let's examine a specific example. In this example, cyclopentanone undergoes condensation with dimethylamine to yield the corresponding enamine. If water is driven off during the reaction, the equilibrium favors the enamine, which is formed via the hemiaminal. The hemiaminal is produced when the carbonyl oxygen is protonated, and the amine subsequently attacks the electrophilic carbonyl carbon. This displaces the carbonyl pi electrons onto oxygen to neutralize its charge, and the ammonium ion that results loses a proton to the medium, providing the hemiaminal. The hemiaminal is then dehydrated to to form the enamine. This happens when the hydroxyl group is protonated and water then dissociates from the substrate as a good leaving group. The carbocation that is formed from this dissociation is resonance stabilized by the adjacent amino group, and the iminium ion sheds a proton to the medium, that proton being lost from the alpha carbon and resulting in the formation of the enamine. In aqueous acid, the equilibrium is driven in the other direction, toward the hydrolysis of the enamine. This also proceeds via the hemiaminal, which is formed when the enamine is first protonated. This protonation occurs so as to form the more stable, resonance delocalized cation. Water then nucleophilically attacks the electrophilic carbon of the iminium ion, displacing the pi electrons onto nitrogen and thereby neutralizing its charge. The oxonium ion simply loses a proton to the medium to form the critical hemiaminal intermediate. And this hemiaminal subsequently degrades to cyclopentanone and dimethylamine. This occurs when the amino group is protonated and then dimethylamine dissociates from the substrate. The cation that is thus formed is resonance delocalized, and the resonance structure in which all atoms possess a complete octet is the more stable resonance structure, and therefore a primary contributor to the resonance hybrid. When we shed a proton from this resonance form, cyclopentanone is reformed. In summary, enamine formation takes place between a ketone or aldehyde and a secondary amine. Gentle acid catalysis is required. To form the enamine, water is driven off to push the equilibrium in the desired direction. But when enamine hydrolysis is preferred, aqueous acid is used, and the presence of excess water pushes the equilibrium in the opposite direction toward the ketone or aldehyde. It could be very helpful to compare the mechanisms in this video to those in the imine formation and hydrolysis video. The sole difference between the formation of an imine and an enamine is whether or not the nitrogen atom has a proton to lose in the last step of the mechanism. Seeing the similarities between these two mechanisms will make it much easier to learn both of them. Here is an explicit comparison of the final step of imine formation to the final step of enamine formation. Notice that in both reactions, an iminium ion is formed, and that iminium ion has two resonance structures. Let's focus on the more stable resonance form, which is the one in which the positive charge has been delocalized onto nitrogen. This is the more stable resonance form because all atoms possess a complete octet. Notice that in imine formation, the nitrogen atom has a proton that can be lost to the medium to create the imine. However, in enamine formation, the nitrogen atom possesses no protons, and therefore the only way to neutralize the charge on the molecule is to lose a proton from the alpha carbon, thereby pushing electrons onto nitrogen to form the neutral enamine. This, again, is the sole mechanistic difference between these two processes. The preceding was an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon or in paperback at a discounted price from Lulu.